A very welcome in today's lecture. I, Dr. Monika Singh, Assistant Professor in Department of Chemistry, CMP Degree College, University of Allahabad, Prayagraj. Today, I am discussing the lecture on crystal field splitting in octahedral complexes. As we know, the crystal field theory was first proposed by Hans Bethe in 1929. It was to describe the bonding and coordination complexes and to rationalize and predict some important properties of coordination complexes like that of color, magnetism, etc. Actually, this theory was purely based on electrostatic interaction between the ligands and the metal ions in the complexes. So, unlike the valence bond theory, this theory has no overlapping of the orbitals, but instead of overlapping, there was the electrostatic interaction. We can say that the ligands either are dipolar molecule or neutral ligands or negative ligands, they got interacted with the metal ions which were positively charged. So, in various geometries like octahedral, tetrahedral, square planar, etc., how the interaction takes place, we are going to study. But in this special lecture, I am taking the case of octahedral complexes. Further, subsequent modifications were proposed by J. H. Van Vleck in 1935 to show covalency in the interaction also. So, before understanding the octahedral complexes and crystal field splitting in these complexes, we must understand the shapes of the d orbital. We all know there are five types of d orbitals, that is dxy, dyz, dxz, xz, dx square y square, and dz square. Out of these fives, the three orbitals of dxy, dyz, dxz are said to be present. The lobes of these orbitals are present in between the axes. As you can see, there is x-axis, y-axis and z-axis, and these lobes are present in between these axes. So these three sets of orbitals are characterized into T2G set of orbitals. While in the case of dx square, y square and dz square, we can clearly see that the lobes are along the x, y and z axis. So, due to the placement of these lobes, they are present along the axis. These two orbitals are said to be EG set of orbitals. So we can say the d orbitals in the shapes of the t orbitals can be further characterized into T2G and EG set of orbitals. So now when we are going to study about the octahedral complexes, we all know that the ligands here approach along the axis. The ligands here approach along the axis. Here, the d orbitals where electron density is oriented along the axis are clearly seen in the previous slide, that they are dx square y square and dz square. So these EG lobes are placed along the axis where the actually ligands are approaching. Ligands are approaching along the axis. So when the ligands are approaching along the axis, they are getting interacted directly with the EG sets of orbitals, d orbitals. So while the orbitals dx square, y square, and z square having electron density oriented between the axes are repelled lesser by the ligands because they are placed in between the axes. Thus, we can see that the two sets of orbitals, e.g., that is doubly degenerate set, and T2G, that is triply degenerate sets, are formed, and due to this, the repulsion between metal ligands, orbitals taking between seriously in between the EG sets, the energy of this EG sets of orbitals, d orbitals, is raised higher. Let's see this crystal field splitting diagram in octahedral case. This shows that the orbital energies are increasing here. In the free ion state, this we can see the 5 dash representing the 5d orbitals, and here it is written free ion. That is, that this means that at this time no ligand is approached near near the metal ion. So the all the 5d orbitals remains of equal energy, that is, or remains at equal energy, we can say they are degenerate. As soon the ligands are approaching near these d orbitals, these 5d orbitals hypothetically get raised in their energy for some time, and when actually the six ligands have approached along the axis, the energies of these d orbitals changed, and we have earlier discussed that eg orbitals are placed directly in the path of the approaching ligands, that is along the axis. So these each set of d orbitals are raised higher in energy. We can see here that these each set, these two lobes have raised higher in energy, while the T2J sets which were present in between the axes have lower energy. So we can see there occurs an energy gap. This splitting of Eg and T2G orbitals, that is splitting of d orbitals into two sets of d orbitals, that is Eg set and T2G set of orbitals, is called crystal field splitting in octahedral complexes. Here, this energy gap is represented by delta OCT or delta O, showing this is the crystal field splitting energy. This dotted line here in the center shows that here the energy difference, energy gap is zero, and this is known as barycenter. So here we can conclude that we can see that the EG are the high energy set of orbitals placed above the barycenter, while the T2G sets are the lower energy sets of orbitals, that is below the barycenter. Here delta O or delta Q, dq, 10 dq represents the energy separation between the two levels. The EG levels are repelled about by an amount of 0.6 delta O. This is about 0.6 delta O above the barycenter, and while the T2G orbitals are stabilized by an extent of 0.4 delta O below the barycenter. So we can say that the energy gap between the EG and T2G is also called the crystal field splitting energy, and is denoted by delta O or delta OCT, or sometimes by calculated in 10 dq, where delta represents the crystal field splitting energy and O represents in case of the octahedral complexes. So because the overall energy is maintained the energy of the three T2G orbitals are lowered or stabilized by zero point 0.4 delta O, and the energy of the two EG orbitals are raised or repelled by zero point 0.6 delta O with respect to hypothetical and spherical crystal field, or we can say with respect to barycenter. So this is how crystal field splitting takes place in case of octahedral complexes. So we will discuss the crystal field splitting energy in this case later on in next session. So thank you all of you for listening and watching the video. Thank you.